Alexandre Proutiere, who got his degree in mathematics from École Normale Supérieure and engineering in École Nationale Télécom, then PhD from École Polytechnique, and then he's been at a number of places, including the Ministry of Foreign Affairs, Microsoft Research, France Telecom, and now he's at KTH. That's a very interesting work on many areas: bandwidth sharing, cellular systems, issues like network coding, and so on. So, Alexander.
Thank you very much for the introduction. Thank you very much for the invitation. It's a great pleasure for me to be here. My talk is about bandit optimization with large strategy sets, and it's some kind of new topic for me, so I hope I won't say stupid things in front of such an audience. I have to mention that I am also affiliated with INRIA and the links in Paris. So bandit optimization is a very old topic. I hope I convince you today that there are still interesting things to do in this area. So bandit optimization problems are the fundamental sequential decision problems. They were introduced by, as far as I know, by Thomson in 1933 in the context of clinical trials. So the problem Thomson addressed was the following. You have patients arriving at you with sequentially and with the same disease. And each time a patient arrives, you have to select a cure to administrate. So you have the choice between the red and the blue cure. After administrating the cure, you observe whether the patient is dying or is surviving. So in bandit optimization problems, you have a set of possible actions that you have to choose from at each step, and you have an unknown sequence of rewards for each action. You have what we call bandit feedback. It means that only rewards of chosen actions can be actually observed. So in this example, you decided to administrate the red cure to the two first patients, and you observe that they die. You cannot know whether the blue cure would have been effective for these two first patients. And your goal, of course, is to maximize the cumulative reward before your time horizon expires, up to a certain step t. So here you want to minimize or maximize the number of people that survive. Okay. So the problem here is to really find a policy that strikes an optimal trade-off between exploration and exploitation. You have to explore suboptimal actions because of the bandit feedback. You have to explore suboptimal actions to discover what their average reward are. And at the same time, you have to exploit. You have to select most of the time the best actions, the actions that provided with the best reward so far. Yes.
What are actions? Some treatment, medical?
So the actions here are either cure red or cure blue. The reward is 1 if the patient survives and 0 if he dies. Okay.
Choice of the pill is the action.
Yeah. The choice of the pill is the action. Okay. All right. So stochastic bandit problems are bandit problems where the rewards are driven by stochastic processes. And I like to categorize these problems depending on the ratio of the decision set, of the size of the decision set, and of the time horizon. If this ratio is very close to 0, it means that your time horizon is very large, and so you have a lot of time to explore all possible actions, and in turn to learn efficiently and accurately the average reward. So when the ratio is close to 0, and this was the original setup proposed by Robbins in 1952, you are going to explore infinitely many times each action to accurately know or learn their average reward. On the other side of the spectrum, the ratio can be infinite. It means that the set of actions is infinite, and you cannot explore all actions before the time horizon expires. This is a fundamentally different problems because if you think about it a little bit, it looks like a stopping time problem, more than like a bandit problem. These infinite bandit problems have been addressed by Berry et al. In 1997 and revisited by Wang in 2008. And actually, there are some mistakes in these papers, and infinite bandit problems have been solved very recently. But I won't talk about it in this talk. In the middle of the spectrum, you have what I call bandits with structure. It means that the size of the decision state is quite large, and it's apparently not negligible compared to your time horizon. But the rewards associated with each action have some structure. In other words, the average rewards of each of the various actions are related to each other, and you are aware of this relation. And you can exploit this information to, in turn, accelerate the exploration process and do as if the problem was, as if your time horizon was indeed very, very large. The connection between structured bandit problems and unstructured bandit problem can be seen as a simple application of the amazing work that has been done in the 70s, 80s, and 90s on optimal control of Markov chains. And in this talk, I will mainly rely on two really brilliant papers, one by Agraval, Teneketsis, and Anantaram in 1999, and a generalization of this work by Graves and Lai in 1997. So generalization of Graves and Lai is important, and so I will discuss that a bit later. But yeah. So there have been quite a lot of work in bandit optimization since 2005, maybe mainly motivated by the electronic commerce, online advertising, and so on. I have to say that you could remove, let's say, half of these papers just because people were not aware of or did not do the connection with optimal control of Markov chain. So you have a lot of people studying structured bandit problems, but not acknowledging the fact that they are indeed just particular instances of controlled Markov chain. So I recommend to read the tutorial given at ICML by Audibert and Munoz for a complete view on bandit problems. In the original setting, we have unstructured stochastic bandit. So we have, it was proposed by Robbins in 52, sorry. You have k actions or k arms, and action I, if it's selected at time t, generate a reward xit that has a Bernoulli distribution of average mu I. Of course, you don't know mu I. The best action, the one with the best reward, is denoted by I star and provides an average reward mu star. Generally, the performance of bandit algorithms is quantified through the notion of regrets. The regret at time t is the difference between the maximum expected reward you could have achieved minus your expected reward. So in other words, it's mu star time t minus your expected reward from time 1 to time capital T. And the fundamental result by Lai and Robbins in 85, so it took 33 years to solve the problem proposed by Robbins, says that for any uniformly good policy pi, the regret has to scale at least logarithmically in time, and the constant in front of the logarithm is a sum over all possible suboptimal actions of the reward that you lose choosing this action divided by the KL number of the between the distribution of this suboptimal action and the best action. In other words, the number of times you have to select the suboptimal action I is KL mu I mu star times log T. Okay.
This was even in excited not Bernoulli, is that right?
There are some generalization. Yes, I mean, you have to be a bit careful, but generally we consider rewards to be bounded, or at least to have a tail decaying faster than exponential. So you observe that in this lower bound of regret, it's linear in the number of arms. So the title of my talk is Bandit with large strategy set. So it's bad news because it's not going to scale well. And it's also proportional to 1 over. So if you do a Taylor expansion of the KL number, and if arms are very, very close rewards from each other, basically you see that this term scale as 1 over mu star minus mu I, which is bad news as well, especially in, let's say, non-stationary environment where basically there is a smooth evolution of the rewards, let's say, and they may cross each other. And when they cross each other, then the problems becomes very hard. This is what Lai and Robin says. In terms of, so this was the lower bound on regret. This is the performance of the best possible algorithm. Okay. In terms of algorithms, of course, Lai and Robbins, as they did it perfectly. They propose an optimal policy that was not so simple, and the lack of simplicity generated a lot of research later on to find better algorithms. So in '95, Agrawal proposed, let's say, more simpler index policies. So if you wish only to have a logarithmic regret and you don't care about the constant, it's very easy, because it's an epsilon greedy algorithm would do the job. Epsilon greedy is an algorithm that with probability 1 minus epsilon choose the best action observed so far, and with probability epsilon explore a randomly chosen action. And if you let epsilon decay with time, 1 over t, you can show that actually you have a logarithmic regret. Okay, it's not so difficult. Very popular algorithms today is called the UCB algorithm. It's based on an upper confidence bound on the average reward, on the estimated average reward. So it has the index of arm I is the throughput, the average throughput observed so far, plus a term that force exploring arms that have not been explored enough so far. Okay. Very recently, in 2011, Garivi and Capet, of course, I mean, UCB algorithm is reach logarithmic regret, but it's not optimal. It's not the right constant. And actually, they can be quite significant difference between the regret of an optimal policy and UCB algorithm. So UCB algorithm somehow has no, I mean, it's difficult to justify. KL UCB is a bit better because it claims back optimality. It's again an index-based policy where the index of arm I is a solution of this very simple optimization problem. This optimization problem is constructed so that exactly asymptotically the number of times you are going to choose action I that is suboptimal is KL mu I mu star log t. Okay, so very good. Oh, again, sorry. So my motivation in studying bandit problems, because I'm primarily an engineer, is that bandit optimization, it's about really the design of dynamics that converge as fast as possible with minimal exploration to a desired regime in uncertain system and under bandit feedback. And my interest in bandit problems was triggered by applications to communication and e-commerce systems. So if you think of it, all the protocols that we are using today in the internet are heuristic. TCP, random access protocols, rate adaptation, routing, scheduling, and so on. So what people have done so far is they took the protocol that exist, and they study it. Like Frank Kelly took TCP and proved some nice structural properties. But the question really I want to address in this talk is, are these algorithms reaching optimality quickly? Okay? Can we design optimal algorithm in terms of speed of convergence? And this is particularly relevant for wireless system where basically the environment is changing all the time. So if you have an algorithm that is optimal asymptotic, that converge to the optimal point but quite slowly, then it's bad news. Okay, it's not going to perform well in non-stationary and changing environment. Yes.
Just at a high level related to what you're saying in the slide before, so none of the previous policies have the property that from some time onward they make no more mistakes, right? Because the regret's growing like log t.
Exactly. I mean,
so I'm just trying to understand what you
when the decision set compared to the time horizon is very small,
yeah,
you always have to explore.
But even when, I mean, because it's growing like log t, I'm assuming that none of those policies have the property that, like, almost surely there will exist a time onward when they're always doing the correct lever.
No.
Is that not true? Yeah,
So generally, the policies that are developed in real world are non-stationary policy in the sense that they are based on an history that is a sliding window. Okay.
Sure.
And this is smart. This is basically to acknowledge the fact that the environment is going to change, and the world is uncertain. Okay. So from this perspective, the algorithms that are proposed today have linear regret, if you want. Right. Okay. Anyway, so in this talk, I will provide two simple solutions to two structured bandits. The first one is called graphically unimodal bandit problem, and I will explain how this applies to the design of optimal rate adaptation in wireless AO2.11 in AO2.11 wireless systems. These are the protocol used in Wi-Fi. It's a fundamental component of your of Wi-Fi technology today. And the second structured bandit problem I'm going to address is a so-called combinatorial bandit, and I will explain how to apply that to the problem of optimal spectrum access again in wireless network. So first of all, let's start with what we call the graphical unimodal bandit problem. This is joint work with Richard Combe, who is postdoc at KTH, and we use a KAIST testbed run by Yoon, Ok, and Yi. And the paper is on arXiv if you are interested. So in graphically unimodal bandit, you have the set of action is a set of vertices on a graph. Okay, and each have a reward of average mu I, and graphical unimodality just means that there is no local maximum in this graph except at the true max. Okay, so in other words, from any vertex there is a path with increasing rewards towards the best vertex, the one providing the best average reward. There have been preliminary work on this problem by Yu and Manor, 2011, but they have suboptimal algorithm. Okay. So how does it apply to rate adaptation in AO2.11? So let me say a few words about that.
So the rewards are associated with vertices.
With actions. So actions are vertices of this graph, and for each action I, when you choose this action, you get a Bernoulli reward with average mu I. Okay.
So on the graph, forget about actions. You have numbers mu I, and you have a graph.
Yes.
On the graph. So you say that they are allocated to vertices in such a way. It's very difficult.
So basically, I mean, think about a line, huh? And unimodal is this.
Yeah.
That's
on the line, yeah.
So it's so a graph maybe is confusing, but it's needed for the application that I have.
Unimodal graph.
It's unimodal in a graph. So basically, there is a maximum. It's unique, and you have always increasing paths to go there. Okay, that's.
So did you also say the graph constrains your next action?
No.
No. So so the graph is just like side information that's given to you.
The graph is side information, exactly. This is part of the design of the protocol. You'll see later. Okay. So rate adaptation in AO2.11. So in AO2.11, you have what's called rate adaptation. It's a fundamental mechanisms allowing transmitters to adapt the modulation and coding schemes to the radio environment. So you can choose, when you have a packet to send, you can choose from various rates. And in the first standard, it was 8 rates, let's say, for AO2.11g. From 6 to 54 megabit per second. When you choose a rate, you send the packet, and you observe if the packet goes through is successfully received or not. The probability that, let's say, at rate R1, the packet goes through is θ1, and so on. And in turn, the average reward corresponding to each action, and action is a rate here, is just the product of the rate and the success probability. Okay. So we know experimentally, and there are some models that say that actually the throughput is a unimodal function of the rate. Okay. So there is a best rate after if you go further, your throughput is decreasing, and before it was increasing. Okay. So it's really this picture. In addition, we have additional side information. We know, of course, that the probability of success is bigger when you transmit at lower rate because the coding scheme is more robust. Okay, so it's really a unimodal bandit problem, right? Each time you want to send a packet, you have to select a rate, and you have, based on the previous observation, and your goal is to maximize the total number of packets you send during your time horizon.
And the core uncertainty is we don't know the parameters theta I.
Exactly. The unknowns are theta's and mu's, of course.
We know they're ordered, but we don't know them.
We know they are ordered. We know that there is an unimodal underlying structure for mu.
R's unknown, theta's unknown.
R's are knowns, theta's are unknowns. So why did I need a graph? It's because today we are using MIMO technology. MIMO technology is a technology that uses several antennas. So you can use these antennas in different ways. Either you send the same information through both antennas and the signals combined at the receiver, or you can send several, let's say two streams or two packets, two different packets, because you think that the receiver is smart enough to decode both of them simultaneously. So an example of graph that provides unimodality in this system is this one. So here, this line corresponds to a double stream, so you don't send the same information through the different antennas. And this is the single stream mode. In single stream mode, you send the same information, and it's basically efficient when the receiver is quite far from the transmitter, when you cannot send at very high rate. On the other hand, when the transmitter and receiver are close to each other, you can send at much higher rate, and in turn you can use antennas to send different information simultaneously. So actually you have unimodality per line, and you have in the middle, you are not quite sure what is optimal. Is it single mode or double mode? So you have to put some edges between these the two lines. All right.
Alexandre?
Yes.
Is unimodality an assumption for the line, or is it an empirical fact? Or?
No, it's strong empirical and validated by models.
So in this particular case, it's not just theta I, it's theta I times Ri, that's the reward. So
Yes, this is
unimodality of the
this is
product.
what is unimodal. Okay. So the state of the art for rate adaptation in AO2.11 is huge, is as huge as the Bandit literature. The one we are using today is called ARF, it's auto rate fallback, and it's an ad hoc protocol that says that after n successive success, or you send the packet successfully, then you probe a higher rate, and after 2 consecutive failures, you reduce the rate. Okay, why not? There have been adaptive version of this protocol. One of the state-of-the-art algorithm is called sample rate. It was done by a student in MIT, a Biquet, and it's based on the achieved throughput over sliding window. So that's a bit better, and it's exploring a new rate every 10 packets. So you see that this constant exploration is really tailored for non-stationary scenario, okay? And this algorithm, of course, have linear regret. Okay, I will. So the point is that all algorithms are heuristic, and we want the optimal, okay? So the question that and to answer the question, we have to solve the graphical unimodal bandit problem. So the question is, how can the reward structure be optimally exploited when we explore? We know that when we explore, when we send a packet at a given rate, it gives information, or let's say some information, about the average reward of the other that you would have obtained using other rates. And the difficulty is to know how really you should do it. Okay. Yes.
At a high level, so I understand here. So is when you talk about like the graphical model and the edge cost, you're saying if I just tried bandit I and I next want to try bandit J, I have to try some sequence of bandits that's on a path between them? Or is, like, I'm just trying to fully understand, how do the edge costs?
There is no edge cost. I didn't. There is no cost associated to edges. The action are organized in a graph. And the graph is just a structure for the rewards, the average rewards of corresponding to the various actions. And that's it, okay? So there is nothing on edges, okay? So actually this problem was some kind of solved already by Van Kat and somehow, I mean, not directly by the paper by Agraval, Tenetsekis and Anantaram, but by a paper by Graves and Lai in '97 that is quite amazing paper. So they solved the problem of controlling a Markov chain where you have hidden parameters that you don't know. Okay. So let me just review the model. You have a Markov chain, let's say with finite states. Their model is more general than this, and finite action space. Okay. You have an unknown parameter theta that belongs to a compact metric space. And the transition probability from a state X to a state Y is depending on the action you select, U, and the parameter theta that you don't know. Okay. When you select action U, you get a reward when you are in state X, RXU. Okay. Then, to control the Markov chain, you have a finite set of irreducible control laws, G, that are mappings from the set of states to the set of actions. Okay? And the average reward, so actions here are control laws, okay? Because the actions that you take depends on the state where you are, okay? So the average reward under control law G is mu G of theta. Of course, it depends on parameter theta. And you have an optimal control law G star, okay? And your goal is to minimize regret. So the regret is again T, your time horizon, times the best average reward. So the reward obtained using the best control law minus your actual reward in expectation. So it looks very much like a bandit. Actually, very easy to see that all the problems that I've been discussing so far are particular instances of this one. And again, you can derive a lower bound on regret for this for any policy. It is based on a KL number under policy G, and it is based on the notion of bad set. So the bad set, the bad parameter set, so parameter is theta here. The bad parameter set is the set of lambdas that belongs to your set of parameters, such that your optimal policy is not optimal, actually, under lambda, if you change the parameter from theta to lambda. And the mutual information, or the KL number, under the optimal policy is equal to 0. So it means that basically you cannot distinguish theta and lambda when you run the policy G star. And the lower bound is, again, logarithmic. It's log t times a constant. And this time the constant is the solution of an optimization problem that I wrote here. Cg here has to be interpreted as the time you have to explore control law G. And this time, the CG have some constraints that are written here. So it means here, if you understand, that the number of time, if you translate that into the number of time you have to play control law G, it means that the sum of suboptimal policy G times of the time you have to explore G times this number must be greater than log t. Okay. Sorry for not explaining correctly. Okay, this is a very interesting result. Although these optimization problems are sometimes very difficult to solve. Fortunately, in rate adaptation problem, it is very easy to solve. Actually, you can show that for any uniformly good algorithm pi, your regret scale as log t times a constant that depends on the graph. And this constant is just the sum over the neighbors of the best action of basically, if you recognize, it's exactly the same bound for suboptimal action k than you had in the Lai and Robbins paper. In other words, if you understood, unimodal bandit problems are just bandit problems restricted to this set. You take the best action, you take the neighbors in the graph, and basically you restrict the bandit, your bandit problem there. So it's very nice because the performance limit does not depend on the size of the graph. Okay, it just depends on the degree of the optimal vertex. And it's very important in practice because, at least in A02.11 system, because the number of possible rates and MIMO modes is exploding. We have, let's say, 70 to 100. Okay. And in this case, I mean, all algorithms that do not know these kind of things are going to crash. Okay. Yes?
So, can the algorithm be interpreted in terms of how you are exploring on the graph? It's clearly not a local exploration on the graph. It's something else is happening.
So I didn't talk about any algorithm so far. I told you that the best you can do, the best you can do is that you can, if you knew that the maximum, the best vertex was here, you would explore just his neighbors, and the number of times you would explore his neighbors would correspond to the number of times in a regular bandit problem. That's it. But of course, you have to identify the maximum.
Yeah.
Yeah. So this is just a lower bound. Okay. It means that the lower bound is achievable, of course, and it means that these points you can explore them less than log of t. Okay, that's all what's in this slide. Okay. And the proof is trivial when you apply Graves and Lie paper. It's just to identify the most confusing bad parameter. And the most confusing bad parameter for an unimodal bandit is just putting the neighbor of the best strategy a bit higher. And you can show that. Okay. And that's why, of course, this is one of the best, of the most confusing lambda bad parameter set. You have the reverse one where this neighbor has higher throughput than the best throughput. Okay. Okay. So now we could. So now we are looking for a simple and optimal rate sampling algorithm. Okay. So how can we achieve this lower bound in a simple manner? Let's say like a KL-UCB algorithm. So the algorithm will be based on empirical average throughput, so that's normal, okay? It will be based on the notion of leader at time n, which is the action or the rate providing the highest empirical throughput so far. And it will be based on the number of times an action or rate k has been the leader, that I denote by little lkn. And it's not an index policy because there is structure. So if you understood, of course, index policies are only valid when you don't have structure. When you have structure, there is no index policy and things are more complicated. But still, our policy is based on an index, bk of n. That is the KL-UCB index modified. Well, it's basically KL-UCB index. So the algorithm is as follows. At the beginning, you explore all rate, okay, once, to get an empirical throughput. And after that, 1/3 of the time you choose the leader. This is for this technical feature for the proof, but we believe it's not necessary. And the rest of the time, you are going to take the neighbor of the leader that has the maximum index, okay? So in other words, it's a KL-UCB policy where basically you choose the neighbor of one of the neighbor, or you choose in the neighborhood of the current leader. It doesn't say that basically the algorithm is going that way. Eh? The algorithm could jump, okay? And well, the main result of our main contribution, I think, is to prove that actually it is optimal. It's a bit complicated. The proof, I won't say much because the proof is, of course, to decompose the set of times in two sets. The first set where basically the leader is not the right one, so the leader is not the best vertex. And this is the most difficult part to analyze. And the second set of instance is a set of instance where basically, 5 minutes left, okay. Where basically the leader is the right one. But for the second set of instance, you can plug the nice analysis of KL-UCB. Okay. So the first term, actually, we prove that it's smaller than log t. And the second term is smaller than 1 plus epsilon Cj of theta, there is a j missing, log t plus O of log t. Okay. So to prove this, I mean, it's not very fancy and not elegant. It's using concentration inequalities and further decomposition of the set of events. What is strong in our analysis, I believe, is that we have actually explicit second order terms. We know what are the terms in log t. We know actually everything after the log t term. And this is fundamentally interesting and important for the non-stationary analysis. I will say a word in the remaining time. So in the non-stationary environment, the theta, it's more complicated because the theta may evolve over time. So the best decision at time t is k star of t. It's changing over time. And your goal is to track the best decision. So the notion of regret is a bit different. The notion of regret is really defined compared to the algorithm that would know what is the best action at any time. So you want to really surf on the best rate, on the best action. And this is what this regret is about. With this notion of regret, you can show, and this was done by Garivier and Moulin, that you cannot achieve sublinear regret under some mild assumption. Our assumptions here are as follows. We assume that theta of t is sigma Lipschitz, and that we can control somehow the proportion of times the average rewards of different arms are crossing each other. Okay. So now we have an optimal algorithm in stationary environment. Let's do the sliding window trick and try to analyze the algorithm. So if you have a sliding window tau, you implement your algorithm on this sliding window and you want to know what's the regret of the algorithm. And with these parameters, we show actually that the regret per unit of time is smaller than this. It's important to notice that this quantity vanishes when sigma tends to 0. It means that the algorithm is good. It means that we have 0 regret per unit of time when actually the rewards evolve slowly. Okay? So the main contribution there was to make the analysis when the theta t is smooth. Most previous work assumes that the theta of t is some kind of jump process so that the average rewards of various actions are always separated. And this is cheating because it's making the problem much easier than it is really. Because the real problem is when the average throughput of different actions cross each other. And this is why we needed the second term in the analysis of the stationary protocol, is because actually the second term becomes predominant when the average rewards of different actions cross each other. It's not the first one. So you really need it. Okay. 1 minute. Okay, so just to conclude, I mean, a numerical experiment. It's really, I mean, we found it spectacular. This is sample rate, and this is our sliding window version of the algorithm, the red curve, with the same sliding window as sample rate. Okay. These are different scenarios in stationary environment. In non-stationary environment, basically what we did is make people move in the room with their laptop, and these are the traces. These are the average throughput, the average reward for the various at the various rate. And our algorithm is really, I mean, is really sticking to the Oracle algorithm that knows what is the best action at all time, at any time. Okay. Anyway, so I will skip the second part. It's too bad. And I will go to the conclusion. Okay. It's too bad, yes. Okay. So, current and future work. Bandit optimization is really interesting. What is interesting is to notice that nothing has been done really already if you look at this graph, okay, which is the graph with the ratio of the size of the decision set and of the time horizon. We know what infinite bandits were solved like a few months ago. And by solved, I mean you have a lower bound and you have an optimal algorithm, a simple algorithm. And structured bandit, where basically the ratio is 0, have been solved for a while, actually, starting from the work by Anantaram and his co-authors. But in the middle, we don't know anything. So basically, if you have a time horizon that is an action space that scale as your time horizon, there is nothing. Okay, and there are probably nice things to do there if it's tractable. So for structured bandit problems, I showed you that they are mapped into an optimization problem, providing the regret bound, lower bound, and insight into the design of the algorithm. So is there a life after this paper, after the contribution of people in the 80s and 90s? I think so. We are still missing an optimal and simple algorithm for generic control Markov chain without computational constraints. So I have to tell you a little bit that the optimization problem giving the lower bound is very difficult. Generally, it's NPR. So you may ask yourself, okay, what if I have additional computational constraints? What would be the regret lower bound? Okay. The non-stationary analysis is very interesting, I think, from a practical perspective. Okay, I will stop here. And thank you.
Am I correct that you have used the term optimal to mean achieving the best possible asymptotic regret rate?
Exactly.
Not necessarily with the best possible constant in front.
No, with the constants.
With the constant.
With the constant. The constant incorporates everything. Having the log t or the square root of t in non-stochastic bandit is piece of cake.
But you could make another formulation, like in the stationary case, where it's infinite horizon, discounted, small interest rate.
So I didn't mention anything about discounted work, and there have been many work by people around here. I had
criterion is
my criterion was really in my application how many packets am I able to send. The discounted version maybe let's say as a sliding window stuff. I mean it's a bit similar, I would say. So it's interesting as well. Didn't have time to discuss everything.
Ganesh, a question?
How does the constant in your regret bound depend on the graph? Because you can always get tuning modality.
Well, it doesn't depend on the graph. I mean, if the hard problem in the design of the protocol, if you want, is to design the graph itself. Okay.
But for the complete graph, it's always unimodal.
Yeah. Okay. So you have to find the minimal graph providing unimodality, which will basically ensure that you reach the optimal action as fast as possible. Otherwise, if you have the complete graph, then the regret would scale linearly as with the number of actions. Okay. So basically, what really you need to sparsify the graph so that to have a good regret.
Thank you very much.